So our last two videos here in this integrative metabolism sort of learning unit have to do with looking at some graphical data as a way to think about some of the big picture concepts that we've talked about. All right, just going to remind you of where we've been, and if you haven't watched these videos already, maybe consider doing so just so you have the totality of these pictures, right? We talked about, this was a slide that just sort of ran through essentially an entire semester's worth of cellular biochemistry on a 30,000 foot view. And then we had another slide that said, okay, let's map that biochemistry and talk about how different tissues are able to specialize in what they're able to do. So the last two videos here, the first one is going to be talking about the timing of these biochemical processes. And then the last video will be a little bit on regulation and thinking about glucose homeostasis. All right, so the first one here, a little bit shorter, thinking about the timing of fuel metabolism. So what we're going to do every time we look at a graph or a plot is we're going to ask ourselves, what are we looking at? Well, this is just a simple bar graph that's looking at 4 different fuel sources and asking how long can we utilize those. And importantly, what we're going to be able to do is break them into a 3 and a 1. That there's certain fuels that are going to be able to be utilized under anaerobic conditions, and those are going to be the first 3 that we see here. And then we'll talk about ones that are going to operate only under aerobic systems, right? And that's what we have here. And let's remind ourselves when we're talking about aerobic systems, what do we really mean? Well, we mean that oxygen is necessary. When we talked about anaerobic systems, we used sort of the phrase that it was rapid but inefficient. So rapid but inefficient. So you can see that we're going to make, energy very quickly that we have here, but we run out of that energy very quickly. And again, highly inefficient because we can't have that be a sustained production of energy. Once we move into sort of this the aerobic sort of pathway, we become not only efficient, but all fuels become available. So all fuels become available. And here's why. Because ultimately, because we are going to need to take any fuel and make it into acetyl-CoA, and then acetyl-CoA will be able to go through the citric acid cycle, electron transport, and oxidative phosphorylation to ultimately make ATP. But that's going to require us to dip into the mitochondria, and we know that we do not dip into the mitochondria unless we are in an aerobic environment. So that sort of like ties those pieces together. Couple other things maybe to just sort of review sort of a little bit is if we remind ourselves sort of what's happening with glycolysis. So we're going to tie this together in a minute, but let's just review glycolysis really quickly here. Right, so when we think about what we know about glycolysis, and this is not the memorizing all 10 steps, all metabolites, all enzymes, all of that for glycolysis, but when we think about glycolysis and its ability to produce ATP, it produces ATP by substrate level phosphorylation. Remember, that was my abbreviation for substrate level phosphorylation. So again, it's going to rely on glycogen reserves. So again, we're going to have glycogen reserves. They're going to be broken down into glucose. If you are talking about skeletal muscles, it's going to use that glucose locally. If you're talking about glycogen that's broken down in the liver, it's going to be put out into the bloodstream, taken up by GLUT4 receptors, or in an insulin-independent fashion into skeletal muscle. But we're basically going to have then that glucose undergo glycolysis, and the endpoints of glycolysis are pyruvate, but we're going to have elevated levels of pyruvate. And then we're also going to have elevated levels of NADH. And remember, if we want to continue to do more glycolysis, we're going to need NAD+. So here is part of the issue here. And I'm just going to move my stuff over just a tad here. No, we'll just leave it like this. Okay. These two pieces are part of the problem. Okay. is they will feed back and inhibit glycolysis. So again, remembering glycolysis is basically glucose going to ATP. We've got 10 steps, and we produce ATP by substrate level phosphorylation. These guys will feed back and inhibit. Excess pyruvate and excess NADH will feed back and inhibit glycolysis. Okay? Now, tying into another video that maybe you haven't seen yet is we can take and sort of relieve this inhibition if we can do something with that excess pyruvate. So one of the things that we can do with it is we can convert it into lactate, okay? Or we can convert it into alanine, okay? And we've got lactate dehydrogenase chemistry or alanine transaminase chemistry. And doing that conversion to lactate is going to be part of the Cori cycle. Converting it to alanine is going to be part of the Cahill cycle. So again, separate videos that I have on sort of those two processes. But again, having the ability to produce ATP rapidly but inefficiently by glycolysis is important. Okay, but I'm going to highlight now these other two pieces. And there is a hierarchy in order of fuel use. So again, that quick review, we're going to tie back into it in just a second. But when we think about the order of fuel use, okay, if you've got energy, you know, the primary fuel that you want to use is ATP. So again, this is your primary fuel, okay? Number that I want you to remember, it's actually the same number as glucose, so it's easy to remember. You have 5 millimolar ATP concentrations in your body, okay? But I'm going to highlight that ATP must be used locally. Even though the liver helps out with a lot, the liver cannot export ATP to your bloodstream to go to another cell. Each cell has to make its ATP individually. So you have to produce this locally, and you run out of it very quickly. Look at it. In about 4 seconds, you deplete your local levels of ATP. So the next fuel source that we can utilize, okay, is phosphocreatine. So phosphocreatine. Okay, I'm going to highlight what happens here. I'm going to go down to the bottom sort of part of my slide here. This is another way to make ATP very quickly by substrate level phosphorylation, is we can use phosphocreatine. But just like you have limited reserves of ATP, you have limited reserves of phosphocreatine, but this is also why people will supplement. Now, it's not unlimited, but you will see bodybuilders, anybody who wants to sort of do weightlifting will use phosphocreatine, because what you're creating is you are creating an ATP reserve. Remember how substrate level phosphorylation works. You take something that's worth more than that magic number of 30.5 kilojoules per mole, so phosphocreatine is worth that, okay? You convert it into creatine, and you are then able to take ADP, pick up that phosphate, and make ATP. And again, and that's because this is worth more than that magic 30.5 kilojoules per mole. Now, you've used up your ATP. You've tapped into and tapped out your phosphocreatine reserve. Then you're going to live in the glycolysis space, making energy rapidly but inefficiently by substrate level phosphorylation for as long as possible, right? You're going to utilize your glycogen reserves. And if you've got ways to deal with that excess pyruvate and NADH that's accumulating, okay, Cori and Cahill cycles can operate with that. That can get you, in a well-trained athlete, into about the 1.5 minute range. After that point, you have to tap into oxidative phosphorylation. You are a distance runner, you're doing anything sort of long-term, you have to tap into this aerobic pathway in order to be efficient, in order to tap into all fuels. All right, so indicating the timing piece of fuel use.